Okay, continuing with quotient of power. So the example that we saw last had the exponent of the base larger in the numerator. So what happens if the exponent of the base is larger in the denominator? For example, m to the 6th over m to the 8th. I could still apply the rule, subtract the exponents. I would subtract the denominator from the numerator. So I can go like this, m to the 6 minus 8. And then if I subtract 8 from 6, it's m to the negative second power. Still can't leave it like that. I have to remember the property of exponent that we went over yesterday. And then it was a negative exponent. You can't leave a negative exponent in your expression. So m to the negative second would turn into 1 over m to the second. That's one way that you can do it. Okay, another way is if I take the exponent of the denominator and subtract the numerator's exponent. If you notice that the exponent is larger in the denominator, that's where the base should end up, because here's really what's going on. M to the 6th over m to the 8th. If you forget a rule or a property, you could always write everything out in expanded form. So the numerator, m to the 6th, is m multiplied by itself 6 times. And then in the denominator, m to the 8th, m multiplied by itself 8 times. So then what happens, similar to the last example that we went over, 6 m's in the numerator cross with 6 m's in the denominator. What's left in the numerator, it's not nothing. It would be 1, because m over m is 1. And then the denominator, m times m, is m squared. So if you know that the base would end up in the denominator, and how you would know that is the exponent in the denominator is larger than the exponent in the numerator, you could automatically put the base in the denominator and do it like this. So m to the 6th over m to the 8th, still subtract the exponents, but it'd be 1 over m to the 8 minus 6, 8 minus 6, 1 over m squared. So you can do it this way. First subtract the exponents, then make the exponent positive, or you could do it this way if you recognize that the variable is going to end up in the denominator. The base is going to end up in the denominator because the exponent was larger. So it could look like this. A to the m over a to the n, and if you know n is greater than m, like we have here, 8 is greater than 6, then we'll look like this, 1 over a to the n minus m. You would subtract the exponent of the numerator from the denominator. All right, now trying to apply some of the properties that we just covered. So on number 1, I want to simplify each of these expressions. 3 squared times 3 to the 6th. I have the same base here, different exponents, which means I could add the exponents. 3 to the 2 plus 6. Maybe you skip writing it like that and then just go to 3 to the 8th. Anytime the base is a constant or just a number, okay, unless the directions just say rewrite it in terms of the base, but anytime the base is a constant or, again, a number, you want to evaluate that. So you probably need to use your calculator. Remember, on your calculator, it should look like this, 3, and then use this as your exponent button to the 8th power. Okay, so 3 to the 8th, that should equal 6,561 using this on my calculator. Okay, on number 2, notice we have 3 powers here. T to the 4th, t cubed is how you would actually say it. That's t to the 3rd power. And then t to the 7th. So you can just take it 2 at a time. Some of you might be able to simplify this all in one step. T to the 4th times t cubed, you have the same base, so you could add the exponents. So this part right here that I underlined, that's t to the 4 plus 3. I'm just going to do some work in my head here. So that's t to the 7th for this part right here, and then times t to the 7th. Okay. If you can multiply 2 powers together with the same base, you can multiply multiple powers together with the same base, whether it's 3, 4, or more. So I still add the exponents because we have the same base, 7 plus 7, t to the 14th. I can't simplify this any further. Unlike the last example, we could simplify 3 to the 8th because we could do that on our calculators and figure out what that is equal to, t to the 14th, without knowing the value of t, other than it can't be 0, then t to the 14th is as simple as you can get it. And then on number 3, there's actually 2 different ways that I can simplify this. Okay, one is recognizing that the variable, the base 4, since that's not a variable, it's a constant, but the base 4 is both in the numerator and denominator, and the exponent in the denominator is larger. So that's where the base will end up. So I can do it like this. 4 to the 7, that's the exponent in the denominator, minus 2, that's the exponent in the numerator. But what's in the numerator is 1. This 4 doesn't just completely disappear. You have 1 in the numerator. So then we could just subtract in the denominator, 7 minus 2, 4 to the 5th. So 1 over 4 to the 5th. If I'm using my calculator, kind of like yesterday or 6.1 part 1, I want to leave this in terms of a fraction. So instead of doing 1 over 4 to the 5th on my calculator, I'm just going to evaluate 4 to the 5th on my calculator. So if I do 1 over 4 to the 5th, it's going to give me a decimal. So 4 to the 5th is 1,024. It's 1 over 1,024. That's one way that you can simplify. The other way is taking the exact same problem, 4 squared over 4 to the 7th, is just subtracting the denominator's exponent from the numerator. So it would look like this, 4 to the 2 minus 7. 2 minus 7 is negative 5. I actually don't want to leave it like this. Anytime you have a negative exponent, you always want to simplify. So that would turn into 1 over 4 to the 5th. I just won't rewrite it. And then I still want to evaluate that in terms of a fraction. Okay, and then number 4, here's what we want to do. 10 to the 4th times 10 to the negative 6th. I have the same base for each of the powers, so I can add the exponents. It would look like this. 10 to the 4 plus negative 6 is the same as 10 to the 4 minus 6. 4 minus 6 is negative 2. And then I don't want to leave this in terms of a negative exponent, so I take the reciprocal, 1 over 10 squared. And then again, kind of like on our other previous examples, the base here is a constant 10 squared. 10 times 10, you might not need a calculator for that, is 100. So 1 over 100, write it as a fraction instead of a decimal.